this is a MFT or mean field theory for of the Ising model. So if you recall, I think I already drew this kind of plot a couple of weeks ago, but what we really need to solve is this complicated interaction between this spin and other spin and this spin, etc. And there is other spin system here as well, etc. Very complicated structure. And as I already described, we treat all the other spins as but so it's a treating all the other spin as a one big spin variable, which is the essence of this infield theory. So treating this enormous amount of spin as a single spin naturally ignore all the fluctuation in spin variable in this within this the group of all the other spin except for this spin. So this, or we can call this ignoring this local fluctuation. So how can we realize this kind of a treatment? That is the first part of this mean field theory of the Ising model. So it's relatively easy to solve the Ising model when we ignore this local fluctuation. So let's start from this interacting part of the energy system. The subscript in here means that we don't care about this external field thing. We only care about this minus j, so ij, si, and sj. So let's just expand this as minus j. It is exact so far that I think it's better to have this here. So instead of just writing si, let's just write si as si minus average value of si plus si. You may feel that so quite a foolish thing to do, but let's just write down this way. And of course, Sj minus Sj average plus Sj average. I didn't do anything. It's just the same thing, of course. And let's put this way. So you arrange this term as like this. So it's a Si minus averaged Si times averaged Sj and plus Sj minus Sj averaged times Si. And the remaining term is composed of plus Si average and additional term is Si. It's getting weirder and weirder, but believe me, this will give you some important insight. You can take some time to check if this is really correct, but believe me, it would be correct because I just followed the textbook. So the meaning here is that this is a source of fluctuation that I also introduced last week, that the deviation from the average value for spin I. And this is the deviation of the spin J with the reference point of the average value of the spin Sj. And the important thing here is that getting rid of all the local fluctuation, or getting rid of the identity of each spin. So this fluctuation provide the individual spin, the I spins individual fluctuation, and this is a J spins individual fluctuation. So the important assumption about the mean field theory is, first, ignore this local fluctuation by assuming that, well, most of the spin will be around the average value. So let's just ignore this second order fluctuation term. And another thing is that let's just assume that average of Si should be replaceable with this average magnetization variable, and same for Sj. And maybe it's a good time to mention that this mean field theory basically kind of ignoring the identity of each site. All of the sites will be equivalent. Si minus m and m plus Sj minus m plus m squared. So of course here we should use approximation, because at this point we ignore the second order fluctuation. So this one, J, and this minus m squared and minus m squared and plus m squared, so it's the Si plus Sj m minus m squared here. And this was a interaction term only, so the full energy function or Hamiltonian for this mean field treatment would be minus J, the same term, Si plus Sj, and the external field term. So and if you assume the symmetric interaction between I and J, this is a linear term of the Si and Sj. So sum of all the things actually, so this part, let's just move this to next thing. So this part become twice m ij Si. Of course, the m is just a constant here, so it's just moving it here. N plus ij m squared part here. Yeah. And I always emphasize that this interaction term is really complicated. But here, it can be simplified much easier because there's no J term in the summand. So we can actually I think there's some extra factor here. So this term, so there's a site I here, and J become all of the possible interaction there. And we have to sum over all these possible I as well. So this one will be actually the same as sum of I because there's no J term here. It only deals with this Si 4 times right here because this degree of I is 4. And we are summing over all the possible I here. So it's like summing this all the spin variable, but so it will sum over all these things. And in other cases, for example, if suppose this one has a J, this J has a 3 neighbor, then 3 times Sj, etc. But suppose we have a much simpler network, like all the degrees would be the same, or the coordination number Z. Then we can consider the summation as Z times sum of Si. But in this case, the problem is that this summation happen in the viewpoint of I, but also done in J's point of view as well. Because of this, we need to have the factor of F. Because this interaction only has a kind of a number of undirected edges in our terminology. So if we, so this is again gross approximation, because and it's not applicable to network with the different degree. But anyway, we just let's assume this coordination number C. Then the equation, this one Si and plus J. Again, this would be the same. This would be the same because this is the m squared times the number of edges really here. So it's nz over 2. And then the non-interacting term here. So the key point here is that we first start from this non-trivial interaction term, but by removing the local fluctuation and treating the average value as a single value, we actually get rid of all these nonlinear interaction terms. It ends up with the single summation term. This makes all the calculation much simpler. And effectively, actually, it effectively becomes the equivalent to the non-interacting spin. And this was actually, so I put the detailed explanation here, just like this. Yeah, I believe the textbook doesn't really say anything about this, but so essentially this is a network problem for me, so I put the extra explanation here. So we will start from this approximated version of the energy term, but please consider this formalism. By ignoring this local fluctuation, etc., we have this formula, and the final form for this energy function would be given by minus plus h and this one, and the extra term. So this is, I can put this superscript as a mean field treatment. So the mean field Hamiltonian or mean field energy function for this spin configuration would be like this. But if you compare this to non-interacting spin case or paramagnetic case, it used to be like this. For non-interacting spin. So if we compare this formula and this formula, it's quite similar. So we can just replace this external field with this term and additional constant here. But one tricky thing is that there's a m variable here, but actually m variable is this is an average magnetization. But average magnetization is calculated by the partition function, which is calculated by energy function. So it looks like we solve everything, but actually, to solve this m, we need to solve e. So it's kind of a circular argument. So that's why we will encounter soon the so-called self-consistency function. I will give some heads up for this. So if we compare this one and this one, immediately we can notice that the mean field Ising model coordination number C, or in our language is a degree K, really. The uniform degree K, is it equivalent? It is actually equivalent to a system of non-interacting spin the important expression immersed in an effective field of strength J Cm plus H plus a constant term Nj squared. So the only difference is that changing this ordinary external field with this form and the extra constant term. So you may guess that the formalism could be quite similar to the non-interacting system. So, well, this is a mathematically speaking. So if I have a real physical comparison, is that so for non-interacting spin, the situation was each individual spin here would be affected by this large H here, and it affects everywhere. So this was really a collection of this pairwise interaction between these. But for mean field model, this spin would have some kind of, so all the other spins would be considered as this large spin, this large external field, effective field composed of this field. And of course, in this way, we completely ignore the local fluctuation here. So mathematically, it is equivalent, but physically speaking, of course, this is replacing this given external field with this shifted external field. So I put here. So it is actually identical to non-interacting spin, just replacing this one and the extra constant term. So let's calculate the most important part, of course. We have to calculate, of course, the partition function and free energy. Where free energy is just minus kBt times log partition function. So the most important thing is to calculating the partition function. So let's first calculate the partition function here. So this is sum of all the spin configuration and Boltzmann factor given by exponential of minus beta energy function mean field here. So it is a mean field partition function. And we can just substitute the mean field energy function there. So mean field energy function was like this one. So we can just put it there. So it's sign is changed to beta Jn plus beta H. And most importantly, just a single sum of spin n minus half beta n Jn, this one. The simplest one here is, of course, this term is nothing to do with S, so we can just go outside the summation. This is a minus inside the exponential, so we can just split this as a exponential of minus nj so many terms here. And the thing we should actually calculate, but if you consider this thing, as we already did for the non-interacting paramagnetic system, this is a possible state, and this is a linear sum. So this can be recast as a product of I to n and exponential of beta j plus si here. So just simply making this summation inside the exponential as a product outside the exponential. So it's a simple thing. And as we precisely did so far, this one actually si plus minus 1, s2 plus minus 1, etc. So that summation of all the possible states or the products of all these exponential factor would be equivalent to twice the hyperbolic cosine and to the power of n. Because in this case, all the summation can be done independently. And the same for the n different vector. So it's just a n vector. Because this variable si is a plus 1 and minus 1 once for everywhere. So it's essentially it's a exponential of this plus exponential of minus this. So yeah, it's the same. So finally, then we can write down this as exponential of and twice the cosine hyperbolic beta h to the power of n. So this is the partition function of the mean field partition function of the Ising model, mean field Ising model. And of course, the free energy per spin, this one, would be, of course, minus ABT, this mean field. And this is, well, if we put this huge product into the logarithmic function, it's just to split it. For example, this is, of course, this exponential part will be separated as this one, because let's just write down explicitly. This is a exponential of this one and of course everything is splitted like this. So this one and this one to this and this exponent would be in front of here, in front of the log factor. So this will be this part is log of exponential is the argument itself. So it will be minus beta nj squared and plus n times log of is 1. So and beta times kbt is of course 1, and this minus and minus become plus. So this will become simpler, this term, and n is cancelled out here. So minus kbt and log of this one. So the partition function is this. Mean field partition function is this. And the mean field free energy density is this. So in principle, we can calculate everything. Yeah. But there is a very important point you should remember throughout this whole discussion. So that's why I put this part taken from our textbook. So there's an important point. So it might appear that free energy is a function of temperature T and external field H. So far, so good. But you may get the impression that average magnetization per spin, it's a function of the average magnetization as well. But so it looks like it's a 3-variable function, M, T, and H. But as I already emphasized a couple of times, the order parameter M is not really a free variable. M is something that will be decided as a result of the free energy minimization. So this functional form, it itself cannot be determined. It is actually not explicitly determined, but it is implicitly determined. As I already mentioned, to determine the M, we need the energy minimization. So this is an important point. So anyway, let's just calculate some various things. For example, let's consider this average magnetization. And this average magnetization, of course, this is the whole, all the things are mean field regime. And this magnetization is, of course, given by derivative of free energy with respect to the external field, while the temperature is fixed. Then perhaps you attempt to differentiate with this differentiate this function only with this h. But again, as I emphasize, this n is in fact explicitly a function of h as well. So if you really, let's take this. So this is This is F. So you have to be careful that M is also a function of temperature in H. So we first minus, and we have to differentiate this term with respect to H as well, while keeping the fact that M is also a function of T. So it's a simple chain rule times, no, it's H. This one, yeah. And also, perhaps a little bit more complicated term is that plus KBT, while we need to consider the differentiation of this, taking the derivative of this term with respect to H. There is an explicit H term here, but at the same time, you have to be careful about this term as well. So at least let's take a from outside. So it's a log something. So it's a hyperbolic cosine and hyperbolic sine. It should be like this, but it's already fixed. And times derivative of this argument. So the first thing is, of course, beta j c and this differential term and beta itself. So if we just, let's make this reference to different color. Then this term become j, so m become j times b, this one, and hyperbolic tangent plus beta h and minus m, this term, this extra term is corresponding to this one, and all the hyperbolic tangent term is here, and yeah, m times here. So yeah. So I'll just put like this. So this term goes to this one, and this term, this term goes to here, and this term goes to this term. It's a complicated, but yeah. Then, if we carefully rearrange this thing, we can rearrange this term as j times t plus 1 and one minus m would be 0. The final term is this single m is the result of this product of this. So, yeah. Yeah. So this is the form is A times B is 0. So it's either A or B is 0. But this term, this response function, is, it should be 0. Because if it should be the slope should be the positive when it comes to the external field. So if external fields become more positive, then the change of average magnetisation should be in that direction. Even if this becomes 0, this one would be 1 anyway. So the key factor is that because of this property, this term should be 0. Because it's A times B is 0. So it's either this one or this one is 0, but the first one should be strictly positive, so this one should be 0. So the final result is M should be the same as hyperbolic tangent, and this look really familiar, at least for me, because we already know that this M is the hyperbolic tangent of beta H for when J is 0. And let's explicitly write down this as, because M is a function of, to emphasize the fact that M is a function of temperature and external field, let's write down this way. And this is the most important result for the mean field Ising model. Again, here is those recursion or self-consistency relation is still existing, because, well, if you look at this formula, you may think that we solve everything. So we, for given temperature and H, we already know the solution. But the problem is that the M here appears here as well. So to solve M, we should know what M is. But to know what M is, we should solve this one as well. So it's a kind of a, we have to, it's a kind of a circular argument. So this well-known terminology called self-consistency is sometimes called self-consistent and sometimes called self-consistency, but I'm not sure which one is more appropriate. But this is sometimes called SCE, self-consistency equation. So there is no explicit form of M. But one thing you can try is, of course, here. So you have M here, and tangent hyperbolic of beta J and beta H. And of course, you can have this M equal M, of course, or weird expression. Y is equal to M, and Y is then the intersection here should be the solution. This is a typical way to solve this so-called self-consistency equation. We'll get back to that later. But if you keep this formula in your mind, and if you go back to this paper of mine again, so much more complicated but kind of similar formula here. Except for this integration over h and k, this formula is quite similar to the mean field approach. So in this paper, the functional form of this self-consistency equation is much more complicated because of the existence of the non-trivial distribution of h and the degree. The basic formulation is the same. M is equal to hyperbolic tangent of something involving M. So quite similar. So, and the most important thing here is that, so we kind of solve this mean field approximation or mean field theory. And let's see, if we taking the limit of external field goes to 0, then we have a very simple self-consistency equation form, beta j times c m t. And we will put this constant in front of these parts as Tc over T times Mt for some region where, so in this case, Tc become this one because, of course, beta is kBt, 1 over kBt. This argument would be the very similar to the case of a non-interacting spin where we went deeply into this the functional form of hyperbolic tangent, because if we take the limit of a zero external field or the absence of the external field, we have to solve this self-consistency equation. And depending on this temperature, if temperature is larger than Tc, this one become less than 1. And if temperature is smaller than Tc, this one become larger than 1. So what we are dealing with is that simply we can solve this x equal to hyperbolic tangent ax form. There's a trivial solution for this one. Can you guess? There's a trivial solution. Hyperbolic tangent of 0 is 0. So x equals 0 is a trivial solution. And that trivial solution is, in fact, will be the solution representing the zero magnetization. The average magnetization becomes 0, the zero magnetization. So that's always solution. The problem is whether it's a stable solution or not. And the most important point here is that, of course, we know what this functional form of y is equal to x with the slope 1, of course, x and y. And we know that functional form of hyperbolic tangent, not easy. It looks like this. The important point here is that the local slope of this hyperbolic tangent function here. So if we differentiate hyperbolic tangent and x becomes 0, of course you can do that with the differentiation formula, but I will take this Taylor series expansion and get this result. It's kind of cheating, but yeah, but actually it's accurate. So the lowest term of the Taylor series expansion of hyperbolic tangent is just a linear term, so I can do that. Yeah, yeah, partly because I don't remember this explicit form. So it's the square of the sequence of something. Yeah. Anyway, so if we magnify this part, let's magnify this part. X, Y, and we have this. Let's just move this. So this Y is equal to line with the slope 1. So depending on the constant A, the hyperbolic tangent form can have this one or this one. It's better to use this. See, it's not easy to. Yeah. Which one correspond to A larger than 1 and which one correspond to the A smaller than? I put this local slope here. So the local slope of red curve is this, and local slope of blue curve is this, right? So this red curve corresponds to the slope is smaller than 1. And this red curve corresponds to A larger than 1. So very important point here is that if A is smaller than 1, there's only one solution. The only solution would be x equal to 0. But if A is larger than 1, of course, it also has the solution, trivial solution. But as you can see, there are 2 more intersections here. So it has 3 solutions. X is equal to x is equal to 0. And the extra solution, let's denote this as x star and plus minus x star. X star and minus. So the important point here is that this non-zero x is possible for a solution. And let's return to our original problem. Original problem was mean field Ising model was M0 equal to hyperbolic tangent of Tc over T M0. And here Tc is this variable. So here, of course, the slope A corresponds to Tc over T. So if we interpret this as physically, this corresponds to Tc over T is smaller than 1, or T is larger than Tc. And the opposite is this one. Tc over T is larger than 1, or T is smaller than Tc. So this is describing the precisely intuitive notion that for temperature larger than Tc, magnetization should always be 0 in the absence of external field. But for T value smaller than Tc, it is possible to have a non-zero magnetization, even for the case of the absence of external field H. So this is the first mathematical proof that this Ising model can have a phase transition, non-trivial phase transition at this clearly non-zero value of temperature. Of course, we approximate a lot by ignoring all the fluctuation, but the key point is that with this quite simple argument about this slope, we can actually derive this situation. So this is the sum that, yeah, is much clearer. Yeah. So in the textbook, is shows this relative slope compared to the slope 1. And of course, you can see that if A is 0, A is 1, it's kind of borderline. Kind of marginal case. Oh, but marginal case. If local slope is exactly as 1, it still has the one solution, but a very small perturbation would make the solution into 3 solutions. So yeah, it's kind of marginal case. So this is the most important concept in this case. So this is the first mathematical argument that this system, the Ising model, can have a spontaneous magnetization at non-zero temperature with this non-trivial value of critical temperature. It's quite important point. This is all I mentioned. Yeah, this is a graphical way to solve this. Again, you have to be careful that is why we put the emphasis here. F is not really an explicit function of M, but it's an implicit function of M, because M is something we should calculate as a result of the minimization of this free energy. So I will not do this stability analysis as well, but here I said that 3 solutions is possible. So, but if you actually do stability analysis, we can prove that this solution is unstable. So the stable solution here is the non-zero solution, either plus m or minus m. So that is something I wrote here. So for temperature smaller than critical temperature, it is these non-zero solutions are the stable ones, and it's non-zero spontaneous magnetization or the ordered phase. So you can actually have this. It's called bifurcation in terms of non-linear dynamics and phase transition in terms of statistical physics. Of course, in general, if we now re-enter this H term, we have this free energy per spin. And in this case, M should satisfy this constraint. So it's a slightly shifted version of the hyperbolic tangent. So if we include this case, the F now become hyperbolic tangent and beta j plus beta h. So instead of this one, it's not hard, not easy, or this one, because of this shifting, we will have this one, or this one, or this one, or this one. No. M and what? So it's really non-trivial now, but anyway. So again, this F is a two-free variable because M should be determined later. So I would not calculate everything, but if you calculate all the M values for each T and H variable, and we plot this, we can plot this landscape of the free energy. The most important point here is that for before, we had this, for example, for the one-dimensional Ising model, the only singular point is this particular point, 0.0. But now, we have to go back further. For now, not only this point, but there is a series of curve here with this non-analytic part. This is similar to like if you have a paper here, if you fold this paper like this, you will have this structure. So this is a non-differentiable, this kind of structure. Yeah. So there is a non-analytic part even for the non-zero temperature, which is the most important point. Of course, except for this line, that the function itself is analytic everywhere. So the only part where we have a non-trivial phase transition is this along this curve. That is the most important point. And so it's a it developed this cusp point for temperature smaller than Tc, and it's analytic for temperature larger than 1. And we can also write down this calculate the magnetization for spin. So for temperature larger than Tc, there's no phase transition because it's just smoothly going from here to here. But for T smaller than Tc, there's a jump here from here to here. The jump here corresponds to going directly from here to here. And that's expressed like this. So for T is larger than Tc, like these two cases, these are smoothly connected. But for T is smaller than Tc, in terms of external field, there is a discontinuous point here. So it's minus m up to this point, but suddenly jump from here to here at h equal to 0. So there's a discontinuous jump here. So it's this kind of a discontinuous jump is called the first order phase transition or discontinuous phase transition. So you have to be careful to say that at h is equal to 0, the phase transition at t equal to Tc is a continuous or second order phase transition. But at t is smaller than Tc, Hc0 is a discontinuous or first order phase transition. It's kind of similar to this hysteresis curve introduced in the electromagnetism. Unfortunately, not quite detailed, but anyway, it's a kind of similar concept. So the limit of the left limit and the right limit is discontinuous. So that's a similar concept. And one thing we can do, and it will become very important when we deal with the more general formalism, so-called Landau theory of phase transition. But let's take this case, tangent hyperbolic. You already learned this example where Tc is this. And if we actually expand this tangent hyperbolic function as a Taylor series, then of course and there is no second order term because this is an odd function. So the next lowest term is the third order term, and the coefficient is 1/3. So it's a T C and T cubed to the power of third. This is the Taylor series of type hyperbolic tangent is x minus x cubed over 3 or something like that. Yeah. And of course, we ignore the higher order term. The force or higher. then we can have this like what c plus in third, and this is 0. So suppose for t is smaller than tc, we learned that now there is a spontaneous magnetization. So m is non-zero. So it means that this one should be 0. So if we solve this, m should be equal to plus minus square root of this one and t. And tc from below, then we can consider t is similar to tc, but we will keep the term, this one. Then we can replace this one as tc and this one as tc, but not this one. We will keep this one. Then this one become plus minus 3 over tc over multiplied by tc minus t square root. So therefore, magnetization is 0 for t is larger than or equal to tc. But for intentionally, I put the exponent beta here. So if t is approaching tc from below, we have this power law dependency with the exponent beta 1/2 because it's a square root. So for the mean field Ising model, we have this power law dependency of the appearance of the spontaneous magnetization with this particular exponent 1/2. And that is the really important result. And of course, if you plot this t minus t over tc in the horizontal axis, and m, the absolute value of m, as I emphasized here, and take the log scale plot, we will have a slope of 1/2 here. Because so it means that mt is some constant times square root of this one for t equal to tc. So if we take a log, then this is 1/2 of log of tc over t and plus log of c, which is just an intercept. Let's just put this. C. Then can have this one. Then this is sometimes we call this tc minus t over tc as a lowercase t. or the horizontal axis here. So yeah. And this is log scale, so of course the slope is 1/2. And we can calculate other quantities like susceptibility per spin with the what many textbooks says a little algebra. We can derive all the necessary quantities. So by this quite non-trivial calculation and using the Taylor series expansion, we can have this power law behavior again. And with this exponent 1 here, so we can compare this one and the amplitude, etc., and we can recover this -1 slope here as well.